Hello! In this video, we are going to prove the following theorem. Suppose A is equinumerous with B and C is equinumerous with D. Then A times C is equinumerous with B times D. Okay, so let's start by supposing A is equinumerous with B and C is equinumerous with D. And our whole goal now is to deduce that A times C is equinumerous with B times D. And what that means is we want to find a function from A times C to B times D that is bijective. Now, since A is equinumerous with B, what that means is there is a function from A to B that is bijective. I'll call that function f. And similarly, since C is equinumerous with D, we know that there's a function from C to D that is bijective. I'll call that function g. And now, we're going to define a function h from A times C to B times D. And it's going to be given by the following formula. So, we defined a function h from A times C to B times D, and it's given by this formula. Now, I think you guys can see that if we take any element of our domain A times C and throw it into this function, we do in fact have that h of A comma C is an element of B times D. So yeah, we do actually have a function h from A times C to B times D. But really, we want to show that h is a bijective function from A times C to B times D, because that will prove that A times C is equinumerous with B times D. And to do that, we're going to show that h is both injective and surjective. Let's start by showing that h is injective. So what does this mean? Well, it means this. To show that h is injective means we want to prove that this statement is true, right? We're trying to show for every two input values to our function h, if their output values are equal, then the input values are equal. And we're trying to prove a statement about every two elements in A times C. So give me any two elements of A times C. I'll call them A1 comma C1 and A2 comma C2. And with these two arbitrary elements of A times C, we want to prove if this is true, then this is true. So let's suppose this is true. And our whole goal now is to deduce that A1 comma C1 is equal to A2 comma C2. Okay, so to start, we know that h of A1 comma C1 is what we have up here, just replacing A with A1 and C with C1. So really we have that h of A1 comma C1 is equal to f of A1 comma g of C1. And similarly, h of A2 comma C2 is just f of A2 comma g of C2. And really, since h of A1 comma C1 is equal to h of A2 comma C2, that means f of A1 comma g of C1 is equal to f of A2 comma g of C2. So really, we have two ordered pairs equal to each other. And if you recall, what that means is that the corresponding coordinates are equal to each other. So really, we have that f of A1 equals f of A2, and g of C1 equals g of C2. But now notice, we can apply the fact that both f and g are injective. So really, because we have two output values of the function f equal, their input values must be equal. So really, a1 is equal to a2. And similarly, we have two output values of the function g equal to each other, so the input values must be equal. So really, c1 equals c2. And really, since a1 is equal to a2 and c1 is equal to c2, we can take a1 comma c1, replace a1 with a2 and c1 with c2. So really we have that a1 comma c1 is equal to a2 comma c2. And that is exactly what we wanted to show. So putting this together, we started with two arbitrary elements of A times C, and we assumed that the output values of the function h are equal. And from there, we deduce that the input values must be equal. Since these two elements are arbitrary, we have proven precisely this statement. And this amounts to proving that H is injective. Okay, so I had to move back up to the top so that we would have enough room. And all this ... means is I'm saying there's more details that came before this. Okay, so we've shown that H is injective. Now we're going to show H is surjective. What does this mean? Well, really, we're going to show for every element B, D in B times D, there is an element A, C in A times C, such that H of A, C is equal to B, D. So really, this is what we want to prove. And we're trying to prove a statement about every element in B times D. So give me an arbitrary element of B times D. I'll call it B, D. Our whole goal now is to deduce that there is an element A, C in A times C such that H of A, C is equal to B, D. Okay, so to start, we know that this means B is an element of B and D is an element of D. But now we can use the fact that both F and G are surjective, right? If you recall, what that means is for every element B in B, there is an element A in A such that F of A is equal to B. And similarly, for every element D in D, there is an element C in C such that G of C is equal to D. So really, since B is an element of B, we can choose some element A in A such that F of A is equal to B. And similarly, since D is an element of D, we can choose some element C in C, such that G of C is equal to D. But now notice, A is an element of A, and C is an element of C. Therefore, A, C is an element of A times C. And since H is a function from A times C to B times D, this means A, C is an element of the domain of H. So really, we can take A, C and send it into the function H. We get that H of A, C is equal to F of A, G of C. And we know that F of A is equal to B, and G of C is equal to D. And now, we see that there is an element A, C in A times C, such that H of A, C is equal to B, D. And that's exactly what we wanted to prove. And since B, D was an arbitrary element of B times D, that means we've proven precisely this statement, which amounts to proving that H is surjective. So really, we have proven that H is both injective and surjective, which means our function H is bijective. So really, we found a function from A times C to B times D that is bijective. So by definition, this means A times C is equinumerous with B times D. And so this completes the proof. And so yeah, that's pretty much the idea of how you could prove this theorem. So yeah, that's pretty much it for this video.